let's begin our new topic today. What is the password? It's PyTorch. Okay, let me type in the, here's the reminder again. Tomorrow morning at 10, I will give a seminar talk using the same Zoom ID, and the topic is about a practical guide to PyTorch, usually for machine learning beginners. But I think I'm going to give it a pretty brief, and I'm doing that as in a as comprehensive way as possible, so that's the paradigm of how we do machine learning research can be depicted in a clear style. Okay, so the password is PyTorch in lowercase and same Zoom ID as our class. All right, so our new topic today is support vector machine. Okay, and this is, I think, one of the most difficult topic or thing to grasp, to master at once. So before, and I can talk more about the origins of this method. So I'll talk about the brief history about this methodology. It's a very popular. It was a very popular mainstream method before the current deep learning technology becomes the dominant ones. So maybe before the year of 2010, or 2012, even before 2012, I don't think there's a whole lot of people in academia using deep neural networks to tackle the supervised machine learning tasks, because deep learning techniques basically have a very hard requirements on your computing resources, on your hardware, on the highly advanced GPUs and CPUs as well. So before that time, when we have very limited resources, and also people don't have people are not convinced yet about the power of deep neural networks, support vector machine and its variants in the so-called field of kernel methods are kind of what most people are doing for for supervised machine learning tasks. Okay, so but even nowadays, although we have for example, for the image recognition tasks or image classification tasks, we know that the convolutional neural network based deep learning techniques is certain to be the state of the art. But still, this method, support vector machine, SVM, is something that people would like to try as a very simple baseline model in a lot of scenarios. Okay, so especially when your data is not big, and when you are not sure if the deep models is the best choice. If you have, say, you are limited by a resource, you are limited by the time to train a model, and you want to see if smaller models or if traditional methods like SVM can do the task, then it is something you definitely want to try, because this is a quite mature technique, and there are a lot of tools, software packages that are in basically in the off-the-shelf style that you can download and use upon data sets. Okay, so I still believe this is a something that should appear in a machine learning course. All right, so much for the history and the little background, and this is the basic outline of the lectures today, and I'm thinking about we better split it into two lectures, at least two lectures. So today I'm going to have a review of the knowledge that will be needed in order to understand what SVM does, what a SVM model does. So we'll review some terms and concepts in mathematics, and basically primarily about the concept of optimization problems, especially the optimization problem under a constraint. And then we will formulate the problem or motivate the problem of SVM by looking at the concept of decision boundary, okay? And the distance between the data points and the decision boundary, okay? And that distance is conceptualized by the so-called margins, okay? And we'll see that the idea of SVM is actually built on top of the measurements of the so-called margin, okay? And in the second half of the lecture, which we probably gonna put it into next week, we will go into the details of how we solve SVM model as a constrained optimization problem, okay? And we'll look at some variants of it, like the kernel methods that we're gonna talk about. All right, so let's enter the preparation part. Well, let's look at what knowledge we're gonna basically use. I see a question: if SVM require less computational processing power, what are the primary advantage of using deep learning today? That's a very good question, okay? Because deep learning is capable of discovering or identify the hidden patterns in data that in most cases SVM is not able to capture. For example, given a face image or image of basically any kind of object, the deep learning technique is basically a stack of multiple layers of neural networks, and the neural network at different layers, they have different functions. They each captures a representation of that level, okay? So maybe the first layer neural network is capturing some lower level features of a face image, and the layers at the later stage capture some higher level patterns or higher level features. For example, the lower layers, the lower features are like lines, colors, but the higher levels capture the shapes, the distance relationship stuff. So because SVM is still a shallow model, it is just not that efficient, or it is not able to capture complex features or hidden patterns. That's what I answer to this question. Anyway, let's look at the knowledge that or the terms and concepts that we need to have a brief review about. So constraint optimization. So this is a term in mathematics, and it refers to the process of optimizing an objective function, okay, with respect to some variable, and in the presence of constraints on those variables. Okay. We are actually had some experience about this process described here, because when we examine the cost function of linear regression and the logistic regression models, we define the cost functions like this, right? And these are actually the objective functions, and these functions are defined with respect to some variables like the theta or the w and b's. But the difference is that previously we didn't set any constraints on theta or w and b, right? They are basically free variables. The resulting thetas and wb's, in theory, they can lie into a arbitrary range. We didn't set any constraints on that. We didn't say that theta should be greater than 0 or something, right? So that makes the no constraints makes it easier to actually optimize the cost function. We simply use gradient method, right? We simply take the derivatives of the cost function with respect to the parameters, okay? And things are more complicated when there's some constraints present here, okay? So the way to, if we want to solve a constraint optimization problem, we need to use a technique called Lagrange multiplier, okay? And Lagrange, or Lagrange in English, Lagrange is a name of a French mathematician, okay? And actually this is, we will start from the simplest case of the constraints that we are faced with. So when we have only equality constraints, okay, that is typically in the form of equations, we can use a Lagrange multiplier to solve it. For example, we want to maximize some function f of x and y. So x and y's, they are the variables. You can think of it theta or w or b. They are just the parameters or variables that we want, that can change, and we want to find the x and y's that makes the function f has a maximized value. Okay, but it comes with the constraint that the second function, g of x and y, should always keep 0. Okay, let's consider this as our constraint. And it is in the equality form, so that's why we call it an equality constraint. If in this case, so if the constraint is an equality, then it's quite easy to solve it, right? We consider the let me go back to this slide. So we basically, if we draw f of x and g of x onto a 2D space plane, okay, because that is the dashed lines here is of the blue, in the blue color is basically the contours of the function f of x. So if there is a third dimension z, okay, that represents the values of the functions, and z is pointing towards you, if you're looking at the slide now, okay, then we are basically looking at from a top-down perspective. We're looking at the contours of the two functions, okay, and it's basically the task is to find the points within this 2D space plane that maximize the values of f, but we need to keep in mind that we are working along the red line, right? Because we need to satisfy the constraint that g of x and y equals 0, okay? And if we use the red line, the red solid line, to indicate all the points that satisfy these constraints, then we must work along this red line, right? And we need to stop whenever we have maximized the value on f of x, on the f of x and y. Okay, so that is the basic layout of the problem. And the Lagrange multiplier function method, the intuition behind is that if we reach a maximum points of the f function, I see a question: will this technique work on only on classification problem? So the SVM methods, or the SVM, I would say SVM method works also on regression problems, something we call the SVM regression, but that is not as common as SVM applied to classification problems. And in the lecture today in this course, we are not talking about regression problems, but we use SVM for classification problems. And actually the development, the original creation of SVM is based on top of classification problems. Okay, let's keep on to this intuition behind the Lagrange multiplier method. So the thought is like, if we reach the maxima points of x, then that means fx should not increase in any direction of its neighboring points. That is the definition of maxima, right? If it still increases towards some direction, then we actually should move towards that direction, right? And suppose that we walk along the contour lines, right? We are walking along these red lines, okay? And a contour line is a direction that is perpendicular to the direction of the gradients. So if you look at the arrows here, okay, the dashed arrows, right, is the gradients of the f function, and the red is perpendicular to the contour lines. So let me draw a contour direction as this one. Okay, so that is the direction of the contour lines. So the direction of the gradients is actually perpendicular to this blue contour direction. Okay, and we want to find the points where f does not change as we walk, because if it still increases or decreases, then that is not the maxima points we want to reach, Right? Say, if we look at these points, doing red, a blue dot here. If we walk towards this direction, right, and the contours of f on these points should be something like drawing a ellipses right here. Okay, so the contours of f should be something like this. So if we look, if we going along this blue direction, then the direction actually will change the values of f, because we are not in parallel with the contour of the f, right? We're going that inside direction, and the f will change because that is in parallel with the gradients, and the gradients represents the function, the direction that the function is increasing, right? And the opposite of gradients is the direction of decreasing. So we want to find the points where the f does not change as we walk. So in this example here, it is the points indicated by the triangle here. And in these points, the f does not change, and the contour lines of f and g, they are in parallel here. So we can basically come to the conclusion that because this is the point where f doesn't change, so this is the maxima that it could be the maxima that we are looking for. Okay, we don't know whether it's the it is the minimum points or the maximum points, right? Because it could be the valley or the peak when the values of the function doesn't change. Okay, so anyway, we can use the relationship between the gradients to find the point where the contour lines are in parallel. Okay, because the contour lines, because the gradients are perpendicular to the contours, and if the contours are in parallel, then the gradients are also in parallel. Okay, so and the gradients, we think of it as a vector, because now in this example, the variable of the function is a vector of two components. We have x and y, right? So the gradients of f and g, they are in parallel, means that we have this equation, and this equation should be satisfied. The gradients of f with respect to x and y should be some scalar number times the gradients of g with respect to x and y. And this lambda is a variable that we want to find, right? And this is a so-called lambda, the Lagrange multiplier. Okay, so introducing a third Lagrange multiplier, third variable is a first step of solving this constraint optimization problem. So if the contour, they are in parallel with each other, that is the points where the target function, where the f function doesn't change values. Okay, so it could be the minimum point or it could be the maximum point. So basically, we want to check the values. We want to compare. If there are multiple such points, we need to check the values of them. Yeah. All right. So let's continue with this Lagrange multiplier. So now we have basically converted the original problem into a Lagrangian expression. Okay, we have this Lagrangian expression. We create a new variable, lambda, and use the f function, subtract the lambda times the constraint function. Our constraint is inequality expression. Okay, so we just need to solve. We just need to take the derivatives of the new Lagrangian expression. So you can think of it of a new function, but this new functions has one extra variable, which is lambda. Okay, so it has 3 variables here. And we take the derivative of the Lagrangian expression with respect to all 3 variables, and we let the gradients to be 0. Okay, and this basically results in these 2 equations. Okay, and we need to solve the equations. We have 3 equations for 3 unknown variables, and in that way we can solve lambda first, and we also solved. We also have a solution for x and y, and x and y refers to the points in which the points that make the f function has its minimum points or maximum points. Right. So let's look at this concrete example. And our goal, look at the problem. Okay, so our goal is to maximize this linear function. F is the summation of x and y. Okay, it's in the 2D space, it's basically a plane. Okay, and we want to we have the constraints that the g of x and y in this form should be 0. So this form of function means that x and y should lie onto the circles, right? Because x squared plus y squared equals 1 means that they are of the same distance towards the 0 point, right? So we're basically we basically want to try to find the maximum points on the plane, but with some constraints that we need to also find the points on the circle. Okay. So if we apply this method of Lagrangian multiplier, we can construct the Lagrangian expression in this form. The Lagrangian of x, y, and lambda is fxy minus lambda times g of x, which is this form, right? And then we take the derivatives of this Lagrangian with respect to all 3 variables, x, y, and lambda, and makes them 0. When we take the derivatives with respect to x, then y and lambda, they are treated as constants, and similarly for y and lambda. Okay, so we have these 3 equations, and we solve it. It's quite easy to solve. We can see that the solutions, we have 2 solutions. The lambda could be 1 over square root of 2, or the negative 1 over square root of 2. So that corresponds to the 2 points here. Okay, that 2 points, one of them is a minimum point, and the other one is a maximum point. So we need to compute the function, the value of the function f on these 2 points, and then decide which point we want to choose for the maximum point. Right. So that is I think a simple example of how Lagrangian multiplier works. In the case of for constraints that are in equalities, okay, the constraint is a equality, okay, something equal, some function equals 0. All right, so that is the first piece of knowledge. We get to warm up a little bit here, and next, things are getting more complex, because in some other cases, the constraint is not necessarily an equation, an equality, but it could be an inequality. It could be something, for example, and we also can have multiple of such inequality constraints. Say we have m of such constraints, and each constraint is a different function, and each function should have non-positive value, it should be less than or equal to 0. That is the inequality constraints that we have. And to solve this type of constraints optimization problem, say our goal is to minimize the function f, then we need to first construct some auxiliary functions. Okay, so I will skim through this these few slides quickly, and it's okay if the picture doesn't connect all at once. So you will need to take some time to go through these slides, and if you want more detailed information, you can go to the link here about Lagrangian duality method. But this method is basically is optional to understand all the details. But this is the key step of solving the SVM optimization problems. So we'll go through the main part, the backbones, very quickly here. So to solving this minimization problem with a bunch of inequality constraints is equivalent to minimize this auxiliary function. We defined something new called J. And J has two cases. In the case where the constraints are all satisfied, it's the function itself. And if any one of the constraints is not satisfied, then we define the function's value to be infinity. Okay, that's how we define the auxiliary function. On the next page, we will see the reason why we are doing this. Okay, so we can also use some indicator function, the capital I of something like this. Right, this indicator function is just a more compact expression to this J. Okay, but since the indicator function is not differentiable or discontinuous, so we can use a lower bound of it to approximate an indicator function, and the lower bound of the function is a linear function in which the lambda is greater than 0. Okay, and we can get a Lagrangian for the original problem. Okay, the Lagrangian of x and lambda is something that's greater than 0 that we just introduced, is the target function fx plus the summation of all the constraints, all the inequality constraints. Okay, so this gi is the left side of the inequality constraints. Okay, so then we can realize that if we maximize this Lagrangian with respect to lambda, not with x, but with respect to lambda, will result in the auxiliary function j, okay? Because if all constraints are satisfied, then the g's are negative values. Then in order to maximize the Lagrangian, we need to have lambda to be all 0, okay? So it becomes all these are gone, and it becomes only f of x left. And if any of the constraint is not satisfied, then we can set that lambda to be infinity, so that the Lagrangian also becomes infinity. So that says we can maximize the Lagrangian with respect to lambda, so that we can get the the auxiliary function. Okay, so we kind of do a series of conversions, right? We start from the original goal, which is to minimize fx given some constraints, right? And it is equivalent to minimize the auxiliary function, okay, j of x. And further, the auxiliary functions is equivalent to maximize with respect to lambda of the Lagrangian term, okay? So altogether, combining these two steps, the original problem becomes this duality problem. It is to optimize the Lagrangian with two steps. In the first step, we maximize it with respect to lambda. And then after the lambda is fixed, then we maximize with respect to the other variable like x here. And the results will be the values that minimize the original function fx. Okay, so this may be too much in 1 or 2 slides to digest in a short time, but the whole thing is that we convert the form of the problem. The original form of problem is to minimize something with respect to some constraints, and then we convert it into a duality problem, a minimize and maximize problem with respect to some new function, which we called a Lagrangian. Okay, so that will be a tool that we need to use in solving SVM problems. Okay. All right. So to solve, this is the final slide for the preparation knowledge and for the warm-up. So in order to solve this minimize and maximize problem, we can use something called quadratic programming. When the objective function is a quadratic function, right? We actually have two conditions. First, the function should be a quadratic function, and the constraints are linear function. Then we can use some technique called quadratic programming. And there are softwares that are already implemented for solving this kind of optimization problems. And so in this in the assignments for SVM, which I'm going to release in next week, we are going to use some package in Python that are designed to solve a quadratic programming function. And all we need to do is to tell what the function is, what the quadratic function is, and what the constraints are. Okay. So a general form like this of the quadratic function is like this, right? It is x transpose times some matrix Q and times the x vector again. So x in this case could be a long vector. You can think of it as a long thin variable vector with just one column. And the transpose of X is the result after we lay it down, right? That becomes a row vector. And the Q's and C's here are the constant coefficients we need to provide to the software QP, okay? And the linear constraint means that it is in some inequality like this, and the A's and B's, they are also matrix and vectors, okay? So the software QP will output the X that minimize the objective, okay? So that's the details are something that we will not dive into in this course, okay? And this is actually a very advanced technique in optimization theory, which I guess is a branch of mathematics. And all we need to do is to use or to call such a function. Okay, and we already have plenty of them in multiple programming languages.
Professor, I just want to clarify. So for the objective function, sometimes that in today's class you use minimize. Some of the example you use the maximize. Is that just like the example, or is there any purpose for that?
So when we try to minimize, okay, so in the most cases, in terms of the conventions in machine learning, we use minimization more often because we define the cost, or later in the future slides, in future courses or in future lectures, we'll use the term loss. And the loss is describes the distance or the difference between our prediction, between the model's prediction and the actual outcome. So loss and or cost is something that we want to minimize. So the convention is that the minimization problem is more often used in machine learning, in optimization problem in general, I think. But it's easy to convert the goal of maximizing something into minimizing something, right? If you give a negative symbol onto that target function, then the result of maximizing that function becomes minimizing some function, right?
Okay, so that is why. So when you give us the example before, it is the maximize, right?
Yes, yes. In the circle example, I use maximize, but
okay,
that
makes sense.
Yeah, that is essentially the same thing. If you want to maximize something, you're basically minimizing the negative of that something.
Mm-hmm,
Right?
mm-hmm. Okay, yeah, thank you.
Yeah. So, yes, I think that's so much for the preparation. That's already a lot of content, but these will be used when to solve the SVM optimization problem. So our next step is to formulate the problem of SVM, or actually what kind of a problem that SVM is trying to solve. Okay. All right. So it's a pretty in the history part I mentioned, it's a pretty traditional method, which is first developed in 1995, and actually the first the very original idea is to deal with the classification problem, which is simple and nice, right? When we want to do classification, we are actually separating the data points, okay? We are actually drawing a decision boundary that splits the different data points apart, right? And these data are labeled, so we know what colors they are here when we visualize them, okay? So a decision boundary in the 2D space, so we use the 2D space as an example, with all the data points has two features, x1 and x2, okay? So if we visualize all the data points, they all exists in the plane, in the 2D plane. Okay, so a decision boundary like that can be described by a linear function, can be described by a linear expression like this. Okay, so w1 times x1 plus w2 times x2 plus b equals 0. Here we use w1, w2, and b to describe the direction or the position of the decision boundary here. Okay, so the problem of how to find the decision boundary is something we have solved, something that we can solve by using models like logistic regression, right? So we define the model by letting the outputs of a linear combination of the parameters and the data outputs to some sigmoid function and use the outputs to represent the probability of which class that data should belong, right? So the bound, and to learn the parameters, we need to define the cost and minimize the cost in logistic regression, right? So the resulting decision boundary is also a linear line, okay? Eventually we will get some W and B's, right? Remember when we do the prediction, at the prediction step, after we have trained a logistic regression, we don't necessarily need to use the sigmoid function again, because when the inputs to the sigmoid is positive, the sigmoid will always output some value that is greater than 0.5, right? So in that case, we think that this is a positive example, positive outputs. And if the input to a sigmoid has negative values, then its output is always less than 0.5. So in that case, we say the prediction is class 0. Okay, so the logistic regression is just one way to come up with a decision boundary, right? So another way of veiling the linear separation, right, is to use, or another way to think of whether the linear separation is good or bad is to measure how far apart the data points on the two sides of the decision boundaries, right? So in a decision boundary like this, and if we find the data points that are closest in distance from this boundary, we can have these yellow and the yellow and the blue data points located, right? So if on the same data, but we draw a different decision boundary defined by W2 and B2, and this time, if we find the closest data points, the distance between the boundary and the point is here. And this line is, of course, larger than the two lines here, right? So this boundary, the second boundary, results in larger space between the boundary and the closest data points, right? And also, of course, if we find the boundary in a more proper angle or proper distance, we can even enlarge the boundaries more, right? This time the boundaries is much larger than the second case. So now the question becomes why we need larger boundaries. Okay, so if we want to tell two classes apart, it's an pretty intuitive thinking that we want to have larger boundaries. That is because when you when your boundaries or the margin, so now this is the first time we introduce the term margin, okay? Whether the margin is big or small will result in very different prediction behaviors of the model. So in the case of the model, when the margin is small, the model is more likely to make mistakes. It is more likely to make misclassifications. Okay, so we want large margins, so more spaces are there between classes. Okay, so the problem becomes how we can find the W's and the B's that maximize the margins, right? So now if we use this simple example to show, if the margin is small, right? This is a quite small margin. If we draw the decision boundary like this, then what if we have some new data gained? Then the data here, it is misclassified, right? It is more close to this cluster, blue cluster, right? To this blue cluster, but it is classified as yellow because it's on the left side. And this one, it is also closer to the red, to the yellow cluster, but it is also misclassified. So in this case, if we draw a margin like this, then these two new data points, they will be correctly predicted, correctly classified. That's basically why we want large margins. Okay, so returning back to the problem of how to find the W's, basically the parameters that maximize the margins. Okay, this is a quite practical question, and also it is solvable because with the knowledge of some linear algebra, some geometric thinking, we can come up with a solution in a straightforward style. Okay, so we got to use some notations here. So for a 2D space, the decision boundary is a line as described by the equation W1 times W times x1 plus W2 times x2 plus b equals 0. That's 2D space. So in 3D space, it's a plane, right? We just extend these parts into 3 elements, okay? So for a higher dimensional that has more than 3 dimensions, then the decision boundary is a hyperplane. We cannot visualize a hyperplane that's more than 3 dimensions, but we can think of it, and we can describe it also by an equation like this. And here, it is similar to the 3D space and the 2D space. It's the dot product between W and X, right? Because we first lay down W. If W is a column vector, so we lay it down by the transpose, and then we dot product with the data vector x1, x is which is a column vector too. So that's the notation of representing the hyperplanes. Okay, and we also have labels, data and labels, and this time we use a little bit different notation for the label. Okay, the data x superscript I, y script I is the same as the previous example as linear and logistic regression. But for the label, it is not 0 and 1. Okay, it is -1 and 1. Okay, because this will make our later on measurements, later on operation, mathematical operation easier. Okay, but this is not an essential difference. Okay, so here next, if the decision boundary is described by this linear equation, then for any data points, it must satisfy that the absolute value of that equation should be greater than 0. Okay, it should be strictly greater than 0. So this is the ideal case, because if the data points fall onto the decision boundary, then this expression should be 0, right? But we don't want that to happen. Ideally, we want a decision boundary not to cross any data points, okay? So if any data points apply to the linear regression here, to the linear equation here, the absolute value of it should be greater than 0. That means the value should never be 0. Okay, so that's the ideal case we are looking for. Okay, so if we draw it with using a 2D space visualization, okay, then on the one side, here in yellow color, the labels is -1. And on the right side, with the data points in blue color, the label is 1. And for these parts, we assume that the linear combination's value is less than 0. And for that part, the linear combination has greater than 0 values. Okay, so this is kind of arbitrarily defined because we can, for any data points that are outside the boundary, there are only 2 options, either greater than 0 or smaller than 0, right? So because y is negative here, -1 here, and the yi is 1 here, so we can rewrite the constraints to be like this: the y times the linear combination should have greater than 0 values, and same for here, right? So this is a perfect decision boundary. The condition that a perfect decision boundary that must satisfy, because it doesn't cross any data points. It must satisfy these constraints. Okay. So now here we have another issue. Okay, because a plane can have infinite number of representations. That means we can write a plane in this form: W transpose times X plus B equals 0. But then we can multiply some arbitrary coefficients on both sides, right? That is still the same plane, but a different representation. We can multiply by 100, 50, 200, 2000, right? Any numbers you can think of, that means the representation is not fixed. Okay, that brings some trouble because we need a fixed representation of the plane. So we need to introduce an additional constraint. Okay, so in order to have the representation for the plane fixed, we need to have the additional constraints. And we in order to have these additional constraints, we choose some special data points. Okay, we let x superscript k to be the nearest point to the plane. Okay, and we place the normalized constraint. Okay, we want for the case of that nearest data points, we want the absolute value of that nearest of the linear combination with that nearest point to be 1. So with these additional constraints, we can actually have that we can have the representation for the plane fixed. Okay, so for example, the 2 points here, they are the nearest to the plane. So the values of yi times the linear combination for them, for these two data points, is equals 1. And for the other data points that are farther apart from than these nearest points, the yi times the linear combination should be greater than 1. Okay. And for that, for the blue parts, it's also the same. For they are greater than 1, and only for the nearest points, because we set these normalized constraints, the values must satisfy equals. They must equal 1. Okay. So with these constraints, the decision boundary is unique or has a unique representation. Okay. So with the unique representation of the decision boundary, we can now try to find the decision boundary that has the largest margin. Okay, so it is now time to define the largest margin. Okay, so we know that the margin is basically defined by the distance between the points, between the nearest point to the margin, right? But we will first start from some random numbers or from some random points. Okay, so we need to find the w's that maximize the distance between the nearest points and the plane. Okay, and we will start from the distance from a plane to a random points. Okay, so in the we'll first use a 2D space to demonstrate. So if a plane looks like this, and if we plot it in a 2D space, then we know that the vector w. So remember that w and x, they are all vectors. Okay, so a vector w has its own direction, and w should be perpendicular to the plane. Okay, because right now in this example here, the plane is x1 plus x2 minus 1. Okay, and so the w1 is 1 and w2 is also 1. So we know that the direction of w indicated by the blue arrow is perpendicular to the plane. Okay, so this is something we will utilize in the next step. And for an arbitrarily plane, okay, hyperplane, how we measure the now we're going to prove that this is also true for a hyperplane, for a plane of arbitrary dimensions. Okay, so say we take any 2 points on the plane, x prime and x prime prime. Okay, because they are on the plane, so they must satisfy the equations, right? W transpose times x prime plus b equals 0, and this one is also 0. So if we subtract one equation from the other, right, we would have this. The b's are gone, right? We have W transpose times x prime minus x prime prime also equals 0. So because the x prime minus x prime prime is also a vector, right? The dot product between the two vectors, W and this vector equals 0, means that they are perpendicular towards each other, right? If the dot product between two vectors are 0, then the projections of one vector to the other one is 0. Okay, so they are perpendicular. So because the x prime and the x prime prime is any two vectors that are randomly picked on this plane. So W, the vector W must be perpendicular to the whole plane. Okay, that's how we prove it. And then we're gonna use this quantity to come up with distance, but come up with the measure, come up with the margin. Okay, so now we need to compute the distance between any data points that is outside the plane to the plane, okay, using the W vector. We simply need to take any points on the plane, say x, that's where x is. Then we create a vector, which is xi minus x, and we project that vector to w, right? Because w is perpendicular to the plane. So if we, the length of the projection will be the distance from xi to the plane, okay? And the distance is measured by this way. The distance or the projection is the dot product between w and xi minus x, okay? And we normalize by the norm of w because we make this w a unit length vector, okay? Okay, and it can be further right into this form if we expand w's into the expression, and if we further expand it, we plus a b and then minus b. So there are two parts in the within the absolute value expression. Okay, because this is something we want to use, because the data, the point x is on the plane, so this part is actually 0, right? And what's left within the distance is the part here, is the first part. Only this part is left within the absolute value. So the distance between xi and the plane is this one. Okay. So what if xi is a special point, say the closest data points that is to the plane, say xk, right? It is the nearest, because we already defined that the nearest point to the plane, it must satisfy that the expression should be 1, right? That's something we defined as our additional constraints, okay? So the distance between the distance between the nearest point to the plane becomes this 1 over the norm of w. Okay, so that is the so-called margin that we want to maximize, right? We want to maximize, given the plane, w transpose times x plus b equals 0, and then we want to maximize the margin, which is defined by 1 over the norm of w. Okay. So it becomes a constraint optimization problem. Okay, this is something we want to maximize, and we need to subject to a bunch of constraints, because the closest to the closest distance. So this is the distance, right? The closest distance should be, so the minimal value of this expression should be 1, because that is our additional constraints. Okay, and for any data points that are farther apart than the nearest data points, it should be greater than 1. So that's why we have these minimal operators here. Okay, and because we can further make this conversion of this abstract to the y times the linear combination. So we notice that we makes it a minimization problem, right? So because we are more comfortable with this minimization concepts. So maximizing this term with w on the denominator is actually to minimize the dot product. We move it, we flip it around, right? And subject to this a bunch of inequality equations. Okay, so it's a very well-formed optimization problem with constraints in inequalities. So that's why we need to use the Lagrangian multi-duality problem. Okay, so this will be something that we'll cover in the next lecture. So I think the slides here, these few slides from number 17, actually number 16 to the number 18 is the way we defined the distance between the nearest point to the plane. That's something you can go over for go through yourself for several times, so that the ideas is connected. And then the preparation knowledge, the first 10 slides, 10, 11 slides is something you also better reveal it a bit, because in the next lecture, we're gonna solve the Lagrangian duality problem that maximize the margins. Okay. And that's it for the lecture today. And I will upload this video later, and also have some quiz questions for the first lecture. Thank you, guys.